So without further ado, I'm just going to kick off and just talk through the rationale behind the work that we do. So I think no conversation these days about Alzheimer's disease is complete without mentioning the fact that we may be entering a new era or with the immunotherapies. And I think many people on this call will know that the evidence, such as it is, suggests that these treatments are probably most effective, excuse me, if given earliest in the disease stage. And that really reinforces the need for us to try to identify AD in its very earliest stages. So if that's the context of why there's an importance in diagnosing AD early, we then have to look to what we're doing now and consider whether or not that's possible. We can achieve that aim well. And if we think about what Alzheimer's disease looks like, without going through all the details about the biomarkers, positive and negative, what we realize is as a clinical diagnosis, although there's a gradual increase in biomarker status, there is a point in the disease progress when there become clinical manifestations. And of course, we as clinicians then are very used to the point that we tend to diagnose people at that stage in the disease when clinical symptoms become manifest. The problem with that, of course, is that that's some way down the line from when the disease progress starts. And if we really want to identify AD in an earlier stage, preclinical, in other words, before the onset of symptoms, what we really want to be doing is then looking at something like this, somewhere where there's a confluence between the occurrence of amyloid and tau biomarker pathology, and then some evidence that the brain itself begins to become dysfunctional. And the evidence suggests that this is going to occur years and possibly even decades before the onset of symptoms, let alone dementia. So if that's the ideal detection point, then what that then requires us to do is look at the current practice that we undertake and decide whether or not it's fit for purpose. And the way I formulate this is actually rather akin to what happens in the automotive industry. We're sort of used as doctors and nurses to identify situations and diseases when they're already well established. It's a bit like trying to fix a car when the engine's already broken. But if we're talking about preclinical diagnosis, we have to turn that around because we cannot wait, and we don't want to wait for the system to break down. What we need to be doing is thinking about implementing processes by which we can begin to detect the onset of a problem before there's a full breakdown. So in other words, we're flipping the medical model from one that is reactive, waiting for symptoms and dementia onset, to one that is proactive and trying to identify symptoms, problems with disease, even before individuals that are affected are even aware that they have any symptoms. So if that's the context of preclinical diagnosis, this change around in the medical approach, then we have to question whether or not the tools we have available to us are actually fit for purpose. Everyone on this call will be familiar with the tests that we use in clinic. These are legacy tests. They're traditionally used by all of us in our routine clinical practice, be it the MMSE or the Adam's cognitive examination. But when we look at the genealogy of these cognitive tests, they go back a long, long way. Many people in this call will be familiar with the trail-making test. This is the test when variously considered to be testing attention, cognitive speed, executive function, and it is included in research batteries around the world for cognitive testing in order to detect early AD. The trail-making test was actually devised back in 1944, and this is the world that we lived in 1944. But this is not 1944, this is 2024. And we need to think about some sort of update to our cognitive armamentarium, and we shouldn't really be using tests that are 80 years old, nearly a century old, when the world has moved on so much. But we still are, because there's a great need to refresh how we approach cognitive testing in AD and other dementia disorders. We cannot really be taking into the 21st century tests that are now getting older and older and older, and they're not fit for purpose. But if we are going to do that, it's one thing to say that these tests aren't really fit for purpose, but it's another thing to then deliver something that is fit for purpose. And this is really where we come in with the research that we've been doing. And it's the reason why we can do this is because it's founded on two components. Most of all, the fact that we have the benefits of decades now of cognitive neuroscience weren't available at the time that the trail-making test or early memory tests were initially designed. But we now know an awful lot about brain behavior relationships and the neural basis of behavior around the kind of cognitive processes that become affected in AD. And we also, by the same token, happen to live in a world where increasingly we have access to technologies previously not available to us, but now can be used to test these new neuroscience-driven approaches, which again cannot be undertaken with the old-fashioned traditional legacy pen and paper approaches with which we're all familiar. So armed with that new approach, this rationale for looking at AD and detecting AD in a new way, what my group are focused on for many, many years is the beginning of AD as according to our understanding of the Braak pathology. We know about amyloid and tau. We know that they both accumulate throughout the brain in stages, and we know that tau is of the two proteins. Tau is the one that correlates more with neurodegeneration and with the onset of cognitive problems. We also happen to know from neuropathology that tau progresses through the brain in this kind of sequential fashion, as outlined by Heiko Braak initially back in 1991. We know it begins in the entorhinal cortex, in the medial temporal lobe, and then it spreads probably transsynaptically, certainly transneuronally. It spreads from the entorhinal cortex to the hippocampus, and then spreads on from the hippocampus into the surrounding neocortex, and then by the end of the disease, we see this widespread infiltration that denotes the full-blown onset of dementia. But if we rewind that clock, what we then look for is we look for the entorhinal cortex as this beginning of pathology, this first region within the cortex where we first see AD-related degeneration. So armed with this information, it's not entirely unreasonable to assume that tests that might probe the function of the entorhinal cortex might have some value in detecting AD at the very outset of the disease. And that's exactly what my team have been doing for a number of years now. And it's all been driven by the underlying neuroscience. And I talked about this earlier being a real key development over the last few decades that should really be translated to clinical practice. Back in 1971, colleagues at UCL stuck electrodes in the rat hippocampus and found that there were cells that related to where the animal was in space. From that time, over the next few decades, there's been an awful lot more work, again recording from single neurons within the entorhinal cortex and hippocampus. And on the right-hand panel, what we see here is that these parts of the brain are absolutely full of neurons that all have different aspects of spatial firing, either when the animal is at a certain place, or when the animal is near a border, or when the animal is moving through an environment, or when the animal is turning ahead. All of these are spatial characteristics, and ultimately together, what these represent is essentially a neural code, an engram that helps us understand, and mammals understand, where we are in the world and how we navigate throughout the world. So what that means is we have at the cellular level this beautifully sophisticated understanding of what the entorhinal cortex does, and it's all related to spatial navigation. Armed with that knowledge, colleagues of mine at UCL, Andrea Castagnaro and Neil Burgess here on the top right panel, devised a VR test of navigation based on the function of entorhinal cortex grid cells. And what you see here in the video is an example of someone wearing an immersive VR headset performing our task. Here in the bottom, this cartoon shows what the test is. We call it a path integration or triangle completion task, and the task is very straightforward. Here is what the person sees through their VR headset. And this, in a nutshell, is the task. So this is what you're seeing now. It's a first-person view within the VR headset as worn by the individual. They look around this virtual environment shown within the VR headset, and they are asked to walk towards this cone that's projected within the VR headset. While they're walking in the virtual world, they're also walking in the real world so they don't get sick. Having walked to the location of code number 1, they then walk to the location of code number 2. When they get to code 2, they look around, they'll see another code number 3. And then they walk to code number 3. When they get to code 3, they are then faced with a very simple challenge, which is you now go back to where you think code number 1 was. And the only way you can do that is by understanding and creating a map of the world based on the environmental cues. So again, just going back to the cartoon I showed earlier, this is what it is. You can walk to 1, you go to 2, you go to 3, and then you have to work how to go back to number 1. This is a classic navigation path integrating strategy that relies on entorhinal grid cells and relies on environmental spatial representations. In other words, this is a very sensitive, specific test of entorhinal cortex function. Now, back in 2019, my PhD student in Cambridge at the time, David Howard, undertook this VR test and looked at people with MCI. And what he found was if you tested people with MCI, the error in where they thought code 1 was a lot greater than that of controls. Now, you think that's not entirely surprising. But if you look at this, what you see is actually there's a huge variance in this MCI cohort. Some of them do pretty well, pretty much as good as well as controls. Others do really badly. But we know that MCI is a diagnosis in itself. It's simply a label. It simply says someone has a memory impairment. It doesn't say why they have a memory impairment. So when you then take this group of MCI people and then you divide them according to their biomarker status, which of these have got underlying AD and which of these don't, you see this dramatic differentiation in the categories. Those who have MCI, so they're symptomatic, they have a memory issue, but they don't have underlying AD, they do very well, a bit like controls. But those who've got MCI, even though it's the same MCI as the other group, but they do have underlying AD because they have positive CSF biomarkers, they do very badly. So this is a nice proof of concept that a VR navigation task, when given to a bunch of people with MCI, can actually differentiate those who have underlying AD. In other words, it's sensitive and specific for prodromal AD. And we then took it further within the same body of work. We then asked the question, well, how does that then compare with standard tests? It's one thing to show you've got a good test. It's another thing entirely to show that it's a test that's better than others. And that's a kind of bar that's very hard for many tests to overcome. And what we did, therefore, to the same MCI cohort, we then compared performance across a whole bunch of other standard cognitive tests, be that memory tests, that ray figure recall, free and selective reminding test, that trail making test we talked about earlier. And what we find is that actually when you compare MCI positive versus negative, the area under the curve with our VR navigation task is way, way, way superior to everything else. So in a nutshell, when applied to people with MCI, then actually the VR navigation test based on entorhinal cortex function is not only good at classifying early AD, but better than gold standard tests that are out there at the moment. So this is the first body of work, and we did it in people with MCI. But actually, I said earlier that what we really wanted to do is we wanted to detect the beginning of changes in people before they had symptoms, and others people at risk or people with preclinical AD. And so following on from the MCI work, my next PhD student, Coco Newton, top right, then undertook the same test in people at risk of AD. So they didn't have dementia, they didn't have MCI, they didn't have any symptoms. They were simply a group of middle-aged people between 40 and 60. We tested 100 people all in all, and we then classified them according to their risk for AD, be it in terms of family history, ApoE4 status, or something known as the Lifestyle Dementia Risk Score, which is a kind of basket of things that includes things like BMI, systolic blood pressure, diabetes, and so on and so forth. And in undertaking this test, we then did the same thing as before. We tested their entorhinal spatial navigation, but we also compared it against standard neuropsychological testing. We compared it against spatial memory, and we compared it against standard memory and also other aspects of spatial orientation. Because what we want to do is pick apart and ask the question, is it this entorhinal aspect of navigation that's particularly affected? And the only way we could really do that is by comparing against lots of other spatial behaviors. And what we found is that actually, yes, if you're at increased risk of AD, then you will get worse. You perform worse. And it doesn't matter whether or not this is a categorical variable, in other words, whether or not ApoE4 positive or negative, family history positive or negative, or whether or not it's a continuous variable like this lifestyle dementia risk score. All those people who are at risk of AD, regardless of the risk factor, performed worse on our navigation task. And what interesting we found when we looked at the data further was that there was a very, very strong gender effect. This was driven by men who are at risk, women who are not at risk, not women who are at risk. If I have time at the end of this, I will explain a little bit more about the gender differences, but this is a really crucial point because we don't really use tests that allow for the fact that different genders perform cognitive functions and navigation in different ways. But these sort of data suggest that actually we need to start taking this into account when we're trying to tease apart and identify the very earliest cognitive changes in people who are at risk. When we looked at why people made mistakes and when they can't navigate what's going on with them, what we seem to find from our modeling data is the error arises from people at risk who can't seem to work out angular estimation. They overestimate in their head how far they're turning. And this actually makes a lot of sense because we know within the entorhinal cortex, there's a bunch of neurons that ultimately are involved in computing vectors. That's how we navigate around our world. Our neurons are computing how we get around. They're undertaking scalar computations, vector computations, and in particular, it looks like it's the vector computation that's affected in people with at risk of AD. When comparing against other tasks, what we find, a bit similar to the MCI work, is that this was an impairment in people at risk that was selective to entorhinal navigation. There wasn't the same separation between at-risk groups when it came to spatial memory. There's a four mountains test on the left-hand side. And there wasn't the same separation when it came to other aspects of spatial orientation. This is egocentric spatial orientation driven by the medial parietal cortex. Very important because we know that that part of the brain is also affected early in AD pathology, albeit more with amyloid than tau pathology. Crucially, when we look at memory, of course, memory, the absolute gold standard hallmark manifestation of AD onset. Doesn't matter what memory test we put at them, all these episodic memory tests, these are selected to be gold standard memory tests, very, very sensitive for AD. We didn't show much change. We also didn't show any change across a wider range of cognitive measures. So in summary, if people were at risk of AD, depending on, regardless of the risk factor, they were selectively impaired on an entorhinal-based test of navigation without the same impairment on any other cognitive tests, including those of episodic memory. And what that therefore might indicate to us is maybe this is that turning point. Maybe you have this bunch of people who are at risk. They are decades away from having dementia onset, but they are beginning to show these changes of impaired brain functionality. And it's showing up in terms of an impairment on a task that probes the function of the entorhinal cortex, which is the first area of the brain affected in AD degeneration. So maybe, going back to the slide I showed earlier, perhaps what we're seeing here is that when your navigation starts to go off, maybe that's the point at which you flip from just being at risk of AD actually to having the onset of AD. And that's crucial because if that is the case, that's the sweet spot within the disease process when you want to be giving any anti-AD drugs, because that's when you're most likely to have the greatest chance of delaying any onset, any progression to dementia in future years. But this is these are early data. So far, all we've done is we've looked at a bunch of people who are at risk of AD. They don't actually have AD yet. We'd have to follow them up for many, many years. So what we're doing now, so having shown what we've done so far, what we're doing now is we're taking it in different ways. In terms of trying to prove the concept that entorhinal-based navigation is the first affected first symptom in AD, we're now going to take it to familial AD. These are people who are not at risk of sporadic AD. They are going to get AD because they have a pathogenic mutation. They have a pre-selenin-1 mutation, and the largest kindred of people with genetic Alzheimer's in the world reside in Colombia, north of Medellin. Francisco Lopera is the Colombian PI who's been looking after these people for many, many years now. And there's around 1,500 of them in all. And they've been very extensively characterized over the years, and we kind of know what happens to them. We know that at age 24, they begin to have biomarker changes. By age 28, they've got amyloid PET positive. No, sorry. By age 32, they begin to have memory issues. By age 44, they've got MCI. By age 49, they have dementia. And by age 59, they sadly die from the disease. This is a 100% penetrance mutation. It's been cascading through the generations for centuries now. These people are very, very well characterized, and we're now going to test these people to see whereabouts in the disease process they begin to have an impaired navigation. Our hypothesis, of course, is that this cognitive impairment does occur early and before memory issues. And if we can prove that in the genetic cohort, then that really will go an awful long way towards us claiming that we can probably find the onset of AD. And that, of course, has huge ramifications for treatment. The other thing that has huge ramifications, just to finish off on, goes back to this translational point. I made a big issue earlier about how, from a scientific point of view, it was very elegant and sophisticated to base a bunch of tests around knowledge of the cells within the brain region vulnerable to AD. This isn't just a kind of hypothetical desirable. This is actually practically useful because ultimately, probably the biggest knowledge gap in AD is that we don't really know how AD pathology, molecular pathology affecting neurons, we don't actually know how they cause the clinical syndrome. So we've got all this evidence about molecular biology studies at the cellular level. We don't know how to translate that. How does that relate to people, human beings, not animals, human beings having the disease? And that's a huge cell to cognition knowledge gap that really does limit our ability to find effective drugs. But what I've been saying here is that we're using tests in humans that are based on cellular function. And therefore, as a corollary, what that opens the door to is translational research. And this is the other arm of what we're doing now. And it's a cross-species study, which is funded by the UK Dementia Research Institute. And it allows us to ask interesting questions never been asked before about how you do link molecular pathology with the clinical syndrome. So Karen Duff, top right here, director of the UCL UK DRI, she's the tau molecular biologist par excellence. And with her work, we can look at how the tau accumulates within the entorhinal cortex and how it then moves transsynaptically into the hippocampus, and we can actually follow this pathogenic molecule as it goes through the process. As the pathogenic molecule goes through, we can record from these grid cells and place cells how does the progression of tau actually begin to damage cellular function. John O'Keefe at UCL, who's the guru in terms of single cell recording. We could use electrodes, or we can use a latest generation silicon probes to record from 1,000 neurons at a time. But we need to understand how tau actually affects neuronal function. We can take it one step further. Yulia Krupich, currently in Cambridge, now joining us at UCL from June. We can undertake more sophisticated work, not just looking at stellar recordings, but looking at something like two-photon microscopy, optical imaging. Just in the way human beings can undertake VR, mice can undertake VR. But the difference between mice and humans is that in mice, we can record optically, and this is a panel here showing what optical recording looks like, as the neurons, as the animal goes through a virtual environment, what happens to the neurons? Here you see a panel of CA1 neurons, and this is calcium imaging, so when the neurons are active, they kind of light up. So what we have is we have this situation in which we can actually look at neuronal firing while the animal is undertaking a VR task. And that VR task is analogous to the VR task we're using in humans. So we begin to join up all the dots. We have tau molecular pathology. We look to see how that affects sequentially grid cells and place cells. We then look to see how that in turn relates to behavior on a VR navigation task. The VR navigation task used in animals actually corresponds to the task that I then use in our human population. And that's how we begin together, working across the species, we begin to bridge that gap between cell and cognition. So I'm sorry, I did skip over some of that at length, at speed. I apologize for that. It's hard to cram everything in 20 minutes. But to summarize, I think the case to make the detection of preclinical AD is crucial for future treatments. I think it's one that people probably wouldn't dispute much these days. The evidence shown here by my group and others now is that impaired navigation might be that all-important transition point from being simply at risk to having disease onset. And finally, by using behavioral tests that are predicated on knowledge of cellular activity, spatial behavioral testing may allow us to bridge that knowledge gap between cellular pathology and the clinical disorder that currently represents one of the biggest hindrances to us progressing Alzheimer's disease research and treatment. With that in mind, I'll stop. I know I'm 22 minutes. I've got 3 minutes for questions. I apologize if I ran through that at speed, but hopefully that did make sense, and I'm very happy to take questions for the next few minutes.